All right, let's talk about a new proof technique called proof by induction, which is very useful for proving the complexity of recursive algorithms, among other things. And there's an intimate connection to recursion. But let's first establish what kind of problems in general do proofs by induction apply to. So a proof by induction can apply to a proposition over a set of whole numbers in a sequence. Okay. So as an example, we're going to look at proving the complexity of towers of Hanoi. Okay, so the proposition there is that the number of disks, I'll call it dn, to move is dn equals 2 to the n minus 1. That's what we saw a moment ago, right? So this is the proposition. And it works over all whole numbers n greater than or equal to 1. Okay, so the smallest Tower of Hanoi problem I can have is the one where I'm just moving a single disk from the left peg to the right peg. And then I have the sequence of all whole numbers after that. All right. So here is how you do a proof by induction. So I'm going to show it on the Towers of Hanoi as an example. And just like when we did the proofs for big O of n, we need to gather a few ingredients. So for the proofs for big O of n, our ingredients were we needed to figure out these constants, right? So here the ingredients are also two things, but two different things. So the first one is called a base case, which is the same thing, really analogous to the stopping condition in recursion. So the base case is a verification of the proposition on the smallest possible input. All right. So in our example, this is verifying that d of n equals d of 1 is equal to 2 to the n, in this case 1 minus 1. All right. So 2 to the 1 minus 1, well, that's 2 minus 1. That is equal to 1. Is that true? So does it take one step to move a single disk from the left peg to the right peg? Well, yes. Okay, good. So check. That's our first ingredient. We verified the base case. All right, so let me say step 1. Verify base case. Or I guess I should say established and verify base case, because you need to figure out what is the base case. Well, in this example, the smallest problem I have only has a single peg. All right. The next step is what's known as the inductive hypothesis. Establish the inductive hypothesis. This is analogous to the recursive assumption in our problems. So when we assumed that we were able to solve problems that were a little bit smaller than the one that we had, that's what this inductive hypothesis is like. So in this example, it's really saying that, so for what we're working on now, for weak induction, and we'll do strong induction in homework. For weak induction, this means assume that your proposition at n minus 1 is true. All right. So in our example, we're going to assume that d of n minus 1 equals 2 to the n minus 1 is true. Okay, so I don't know, I haven't proved yet that this in general is true for any n. But if I fix my n, then I can assume the one that's one smaller does satisfy my proposition. So I can assume this. So that's step 2. All right. Let me make these a little bigger so they stand out. All right, step 1, establish a verified base case. Step 2, establish the inductive hypothesis. So I'm going to assume that this is true. And then step 3 is the inductive step. That's what it's called. This will complete the proof. So let me actually give these headings too. Inductive hypothesis. Okay, so base case, inductive hypothesis, inductive step. So in the inductive step, you do something that allows you to move up from your assumption of size n-1 to your hypothesis of size n. Okay? So in our example, we're going to establish what's known as a recurrence relation. So what we remember is that to solve a Towers of Hanoi problem with n disks, well, we first have to move n-1 disks, right? Then we move the biggest disk, and then we finally move n-1 disks again, right? Okay, so I could just rewrite this. I'll combine like terms and rewrite this as this. Okay? Now, so what I'm going to do then is I'm going to invoke my inductive hypothesis. I'm going to substitute in. I actually know by assumption what d of n-1 is. Well, I said that if my proposition is true, then this should be 2 to the n-1 minus 1. All right? So let's just plug that in. So we get 2 times 2 to the n-1 minus 1. And then plus 1. Okay, so I'm just substituting my inductive hypothesis into my recurrence relation that I established here. All right, so this is the equation I get. Now let me just simplify this equation. So I'm going to distribute the 2 through here. So 2 times 2 to the n minus 1, well that's 2 to the n. Minus 2, so I distribute the 2 through here. And then plus 1 on the outside, well that equals 2 to the n minus 1. Hey! Nice, isn't that what I was trying to prove? Excellent. Okay, so what I did was I built up. And actually what you end up getting is a domino effect, because you know this tells me how to, this inductive step has proved that I can go from a smaller problem up to a problem that's one bigger. And where do the dominoes start? Well, they start at the base case. So I've proved that 1 works. Then with the inductive step, I can go to 2. Then from 2, I can go to 3. Then from 3, I can go to 4. And I can go up as big as I want, as long as I'm able to, via the inductive hypothesis, prove with an inductive step that the proposition is true. All right. So that's it. Base case, inductive hypothesis, inductive step. So oftentimes, proofs by induction come to the rescue because they allow you to prove something that looks kind of difficult to prove otherwise. The one downside of a proof by induction, it doesn't give you too much intuition. It's not really a constructive proof. It doesn't really tell you why or how this is working. It just tells you that it's true. You know, with a recursive algorithm, sometimes we can get a little more. Like if we can match these recurrence relations to some intuition we have about the problem, like I told you with Towers of Hanoi, well then we learn a little bit more. Okay. So the only downside of proofs by induction in general, they don't always tell you why something's working. You actually have to kind of know the proposition before you prove it. All right, but you can kind of discover different propositions by experiment. So let's look at another one. So we're going to move towards proving that you know, some evidence that that 2 to the n is little o of n factorial. Remember, so that n factorial dominates 2 to the n, right? Well, actually, I guess we can really actually prove that. So we're not just some evidence, but actually proper proof. So this is not something I was able to prove with L'Hopital's rule directly. If you remember this, when I was establishing the hierarchy, yeah, I could show that 2n dominated any polynomial, and I could show that any polynomial would dominate a log, and I could show you that a log would dominate a constant. So I was able to establish part of the hierarchy, but I never was able to finish showing why n factorial grows more quickly, strictly more quickly than 2 to the n in the limit. But we can prove this by induction. So in particular, let me try to prove that when n is greater than or equal to 4, that n factorial is greater than 2 to the n. Okay? And if we can prove that, hey, we can actually finish our big O proof, because here's one of my constants and the other constant is 1, right? So that would complete a big O proof. Actually, it would complete a little O proof as well, because I guess we could say, well, yeah, this is strictly greater than, and we make an analogy with little o of being a strict greater than. Okay, so this will strictly dominate 2 to the n beyond a certain amount. Okay, so I'm going to wave my hands a little bit with little o, but just see how this is going to help me to establish my hierarchy. All right, fine. So the first step is the base case, right? And what's that? Well, here it's actually n equals 4, right? So we need to verify that 4 factorial is greater than 2 to the 4th. Is that true? Well, 4 factorial. I mean, we got Python right here. 4 factorial is 4 times 3 times 2 times 1, right? And then 2 to the 4th is just 16. All right, good. So that worked. Okay, now let's do the inductive hypothesis. So my proposition is that that 2 to the n is greater than n factorial is greater than 2 to the n. So what I'm going to do is assume that it's true that n minus 1 factorial is greater than 2 to the n minus 1. Okay, good. That's it. That's our inductive hypothesis. Okay. So let's try to do our inductive step. Okay. So how can we use this fact to prove that that n factorial is greater than 2 to the n? Well, in this case, so I already have this inequality, n minus 1 factorial is greater than 2 to the n minus 1. Well, what I can do is multiply both sides by 2. Let's start with that. So this certainly doesn't change the inequality at all, right? I just multiply both sides by 2. Okay, well now I can make the right-hand side, I can actually change that into 2 to the n, right? Okay, nice. So I'm getting there. The right-hand side is what I wanted in my proposition. Now what I would do? Well actually, so if n is greater than or equal to 4, then certainly n is greater than 2, right? I mean, that's kind of a trivial statement right there. If n is bigger than or equal to 4, then it's definitely bigger than 2 also. But what this allows us to do is to preserve this inequality by changing the 2 into an n. All right, so n is greater than 2. So if I turn this 2 into an n, well, certainly this thing is not going to be any smaller than it was before. So it's still going to be bigger than what was over here. So in other words, I'm saying that this implies that n times n minus 1 factorial is greater than 2 times n minus 1 factorial, which is greater than 2 to the n. Okay, so if I really do this out step by step. Well, n times n minus 1 factorial, that is the definition. That is one way to define n factorial. So we've actually finished the proof. So n times n minus 1 factorial is n factorial. That's greater than this, which is in turn greater than 2 to the n. So now we're finished the proof. Oops. I need to use late check there. Okay, excellent. All right, that's it. So I'm going to have you do your own little inductive proof real quick, just to make sure you followed this. I'm going to have you prove the an arithmetic series, which you've taken for granted at this point, but it's the fact that the sum of the first n numbers is n times n plus 1 over 2. So I gave that to you in assignment 2, and you took it for granted, but now you're actually going to prove it. Okay? So that's it.